Oh, Anthony. Hi, Anthony.
Hello, how are you? Can you hear me okay?
Yeah, I can hear you.
It's been quite a while. I hope you're doing well.
Yeah, Tony, yes?
Tony, yes.
Yeah, okay. Yeah, nice to hear. Where are you in Mexico?
No, I'm in Calgary. I think I
Oh,
used to coach your daughter at Southwest United way back when, if you
okay.
remember. Yeah.
That's good. Uh, now she's coaching, actually.
Oh, is she? No way. That's great to hear.
Yeah.
So I saw your tech talk on LinkedIn, and I thought I'd just tune in.
Okay, that's
Yeah.
good. Yeah.
So thanks for having me.
Nice. Thanks for coming. Yeah. Mhm. Okay, let me start with over this development. So the So today is the fifth talk out of this. Every week we are trying to do is to cover all our services as well as the software base and various things. So today it will be about the internal development, which we thanks to our development team, including Valentina, Anastasia, Alex, Jung Jae, like we have full team working on working on this qStrat development and many others which before worked on it. So let's go next slide. So this is the again, as I said, like it's four talks. They are like recorded and on the YouTube channel on the called Petro-Explorers. I will send you a link afterward. And so today's talk will be about automation and log data management and quantitative sequence stratigraphy. It started with the quantitative sequence stratigraphy, but expanded into, because log data is quite messy. So we start cleaning it up and trying to automate the cleaning process. And that is where we'll go through. Then it will be next week, we will go through deep learning, like deep learning and its geoscience application, and then rock physics and pre-stack scenario modeling, which is what we do as a start of any other simultaneous inversion or other detailed projects. You do a pre-stack scenario analysis for the seismic, and then we'll end these talk series with a complete simultaneous inversion workflow, uh, going through the what are good practices in those in the simultaneous inversion. So today, today we will be going through the automation workflow, log data QC, data conditioning, preparation, autocorrelation, age assignment, and then actual the tools which do during that process, all the tools, and then we'll conclude with and have discussion. So as we start every talk with the promoting ourselves is the that we what we do is the we have a reservoir characterization services which come from quantitative and qualitative services, which kind of interpretation and quantitative, combining them together into almost they are should be all together, but coming from the pre-stack side to the post-stack side, combining them into neural networks or various workflows, taking the log data and even now the engineering data and those things coming into the stratigraphy, the cores, all the information from rock physics and those and interpretations in the RGT domain, Wheeler domain, in the age domain, and combining them into the basically hydrocarbon probability cube or output into reservoir models, which they can take about the engineering reservoir characterization takes on from there, or simulations and those. So that is our core area, what we cover. The client base, we have worldwide client base in last 12 years. We've been working extensively in the Western Canada Sedimentary Basin and then Gulf of Mexico, and going down to Colombia and to Argentina, quite a bit of work around here. Then on the east side with Pakistan, India is our core, with a lot of field development plans and various other geological interest. And the more interpretation hub on the exploration areas of rift basins like Chad and the Kenya and Tanzania, or Chad and Nigeria. Like so various areas we worldwide we have certain basins we have a lot of experience, but I'm always looking for new basins as well because similarities are there in SQL stratigraphy and interpretation. So our software base, we, as many of you know, that we are the OpenDetect representative for last 12 years in Canada. So we use all of their plugins and tools and promote, as well as we use as services. We combine many projects with them as well. So it's a combination, very good collaboration with the worldwide access on the DGB. Then for the quantitative work, we use Hampson Russell for inversions and AVO. And then for petrophysics and geomechanics, we use the called DGS software. And in addition, we are start developing what called the sequence stratigraphy workflow or geological workbench right now, but it will extend and combine with the geophysical workbench, which is the OpenDetect side. So from the quantitative sequence stratigraphy, what it really mean is to create a true geological earth model. So true geological earth model means the framework should be age cohesive. So every top should be related to the age, and all those surfaces or peaks should be follow the age, as well as true to the palinspastic true deposition. Once you have the age figured out, then deposition is easy to cut it down into deposition and the lithologies. So sequence stratigraphy being our base of interpretation, like OpenDetect is already from seismic doing a lot of sequence stratigraphy. And then in qStrat, we are writing through the well log process. And in between, we interact with the seismic through taking the information and feeding back the information into the seismic. So this is all cohesive process getting together to have a full time and depth model, as well as full geological model. So it would be true to geology because there are sub-resolution in seismic. There's resolution is low versus the log data, and then you're doing the geological modeling in between. So we will go through this. qStrat would cover this workflow, which is each of them have a much detailed work. So we'll go through these step by step. So just looking at the first step, which okay. So the from log QC, so taking the LAS files, you need to first like kind of resample them, so that because they can come in various sampling issues. So come in resampling, and then taking into as a log QC. So we'll go over log QC, then normalization, then extracting like gamma ray, and then gamma ray log to converting to V-shell. So right now the processes go through the V-shell process, and then we add the deviation. So all the well data have to be, even if they are vertical well, they are assigned X, Y, Z position. Every log sample have to be in its true position in the subsurface. So that is prerequisite, and then usually people take it that afterward, but that have to be addressed. So all the things which could cause problem later have to be addressed earlier. Coming from the age, then we create what called the uh, uh, in the qStrat log, which is our main central program for stratigraphic interpretation, and then going into qStrat correlation, which is taking the qStrat files. And then, so what our qStrat is a workbench, and then I will show you the picture just next. And so it can output the interpreted logs with tops, and then whole sections and maps. So cross sections and maps, which is the whole workflow I will go through during this talk. So our workbench contains a bunch of buttons which have various what you do with the LAS files, and they keep on we're adding more and more capabilities to these. But with the QC analysis, then now LAS file could have different names than the headers and these, so we need to address those areas first as well, that headers which you match with LAS. So we do a lot of search in there to automatically attach the headers. Then we can view file, resample them, despike them, and normalize them to come out with the gamma ray and convert them to VShell. So this is the capabilities to reach the VShell. And then at the same time, we take the well geometry files, add them to the to be convert as we take the VShell or any log file, and then we create our called the qSt. That is the internal format. It's similar to LAS, but to join with the geometry to create the deviated well file. So all the deviated and vertical would have now all that data, and then that goes into our qSt apps. So various apps which are more what geology, fancy part which geology just want to see. But these are all the parts which need a hard work, which geologists usually don't want to do, but they have to. And that's where the time-consuming part comes in. Most of the time, the interpretation part of the logs and those are much less time-consuming than actually fixing all and finding all the log data. So that's what we addressing in the first place. So the log QC is, we can bring in, like these are like 50,000 files from Kansas, like, you know, they all of the Kansas state, they're all the files. So you can run a QC on any number of logs. So you take the LAS, sort and separate them and put them in a full log QC window. So it will go through and create a database. So it will tell you list of logs, list type of log types mapping. So it would do the log type mapping, and then you can convert. Then here you can also log type frequency, which one have gamma ray, which one doesn't have gamma ray, and then summary. So we are expanding these with the log QC template. So the outputs from these is like you have various Excel windows. These are usually, it came up from the idea when the clients usually give us the data. They don't know what they have given, or, you know, whole dump of the data. Then we can quickly, just within minutes, you can output as a database. So the whole of the, that which file have which logs, and if you're looking for a shear log or sonics and or other, you can actually just find out which files, and you can export each of the logs from directly from this log QC window. And and also it exports that the same file with all the details into Excel file. So you can actually look at it or get that, okay, this is the data I received from all the LAS files. And it also tells you what the well and the LAS file name. And so it's kind of creating a whole database. And now we would start working with it. Also, in the same time from the log QC, we can also view any of the log if you want to see what the logs look like. Are they really, DT or these? So that's a log viewer which can work and tell you the data. Not only this log viewer, this is only for the geologist to look at the sporadic logs. You're not going to look at the 50,000 logs or 5,000 logs, what you're working with. You are going to take these whole, as a whole, find out, computer to find out what is the start of the log, end of the log, what are the values range, what are the standard deviation, and all those for each of the log. So there is a whole statistics of each of the logs, and then combining it, then we're going to, of course, combine it with the headers, and I will go through that process. So, but first of all, before going to the next step, in this first step, we also resample the logs. So we want to have a consistent sample rates and consistent going forward to consistent units and consistent sample rates. So in order to do that, we call the log resampling. So in a resampling, you wouldn't change anything except you can step at various methods of interpolation, but you can, if you want to go with a 1 meter step or 2 meter step, that is fine. But usually we go with a dominant step, what you have in the most of the logs coming in. So if it's 0.125, which is or 0.1 meters or half a feet, then we use that as our continue to be our sample rate, and then either in meter or feet, usually depending on the country. Like, if it's Colombia and US, it will be in feet, and if it is rest of the world, probably in meters, except few countries. So but that would be allow us not to get into trouble afterward, because if it's which one is in feet. So we are not want to individually see the wells, but we want computer to do assign and resample. So it takes another 5 minutes to resample everything into a consistent sample rate, irrespective of, we are not even without looking at the data, although we can look at it individual. If there are wider ranges which are completely off, like start and stop depth is very small, it's some other data, or it is not a log data, but it is like a production data which is put as a LAS file, then it will automatically will discard those and move forward only with the resample, which can do. So there are various checks which we defined so that would move forward and in the log database. Then the other thing that all logs can be, it's with the same well, different logs and different runs could have different log LAS names, while and also different information, like so KB, the ground level, various have a slightly different information based on the log run and based on the some bad data coming in, or just a difference between the two files, the header file which we receive from the client, or we preparing. So here it's called the standard header. So the first task would be to sit down and actually extract that information from the header file and from LAS file, and combine the information to take the information from LAS files and go uh, into the final header. So we're taking the information and the same as the a header, save a combined header information as a process. So you can process the LAS files, and then it can also rename. So you can rename the files then to the UWIs or standardized UWI, change the name based on the header file. So you can assign those. So there are a few functions which need to be done in order to be standardize our database. So again, remember, we are not loading the data into anything. We have at every stage the LAS original files plus every directory we create next to go through the next directory. So then the comes in that we extract the each of the logs. So now right now we're dealing in sequence stratigraphy, we're dealing with the gamma ray log. So we take out the gamma ray or SP at various, depending on each of the pieces, we export them as a separate now directory with all the gamma ray for each well. Each well could have more than one gamma ray log running. And so one thing we will start now as a whole project, we'll start normalizing. In the normalizing window, we can actually select the number of wells which we think as a reference for normalization, and using the interval as well. so the normalization process goes, then after you get that mean and standard deviation, you can just put a mean and standard deviation based on the average what is coming in. What you see as various wrong data coming in bad gamma ray file, it will show up as the mean standard deviation being too high. So it means there is something wrong. We need to look at this file or remove the file from our analysis. So analysis, we know few files which would be common, and then we add overall average of the total. It will provide that this is the average, but it could be affected by one or two wells. Uh, that's why we select the wells, take the average, and then do this process of these. So it would be first will be a shift in the mean, like the shift of the log, and then by standard deviation, we will use the original sample value, but we run what called the Savinsky-Golay filter to move the data. You want to use the mean away from the mean based on the overall as a group rather than individual samples, because you can destroy the sample value. So there is a very so it preserves your histogram of the logs, so it does not affect much, but it does normalize to us mean and standard deviation, which becomes really important for impedance, for the modeling, for the normalization process. And as we add more tools of these automations, so this auto normalization will, with one button click, now we reach the next step of a gamma ray once gamma ray is normalized. So once you have a normalized gamma ray, then you can assign based on the V-shell log calculation through a linear formula or combination of Larionov or Steiber or Clavier or various other formulas depending on the deposition, how you want to make. But I would just basically, there is a D-spike algorithm as well before. So we would go through the D-spike so that we don't have any specific spikes left. But this one we take next by various these, and in combine various formulas, how they combine with each other. So taking that to V-shell, now we are going to work in the V-shell domain. That's where things are going to convert into the qST files. Like so up till now it has been in the LAS files. So now we do, next step is take the deviation files so it's a parallel step from the previous. So we take the deviation files and then we create a geometry file for each well, for vertical and for deviated. So you can actually see that in this tool to get automatically, this is about 1600 wells to assign the deviation. So take the deviation file, attach it to all the vertical wells will be, and you can view them in 3D map. On the 2D, you can compare it as this. So this automatically would convert that into a geometry file. So this geometry file now it's going to attach to the LAS file. So we take the then LAS file and attach a geometry to it. So when you attach a geometry, every log point becomes the every depth point in the log, even starting from way close to the surface, you start getting the XYZ value of each of the V shell. So if V shell value, you have the TVD, X, Y, and Z. So when we go to the cross sections or individual logs, we can view them in a deviated or vertical or TVD or MD domain or at the sea level. So all those things, because we need to continue taking every sample. As we said, it's a 1/8 of a meter sample rate. So each of them have a XY position in space. So then you can view it or project it to X or Y. And in the cross-section case, we would project it into a cross-section domain on a seismic, or when you're trying to project it. So this is the step: create the geometry, attach it to the data. Once all that done, so that was the groundwork to produce in order to get understanding. Now that we come into the reference well domain, now we go from there to, we prepared everything. Now we go into the main window. It's called qStrat log. So qStrat log is the program which combines the age, the sequence cycles, the transgressive regressive cycle, and quantitative sequence stratigraphy, which is the method I will explain just in the next slide. That quantitative sequence stratigraphy, how we can quantify the series of coarsening upward, finding upward sequences, as well as increase in sand and increase in shale. And also we assign for each top it's very important that sequence stratigraphy top, although I'm using these, tops of Belly River and Milk River and these, but that is usually in a database coming in, you can pick wherever you would like to call it a Belly River sand, but it does not equal to a same age sand or same age shale or a flooding surface. So that is where we need assignment to be a same age assignment. So we assign for each tops, our tops marker, or what we should be calling age markers. They are not a lithostratigraphic tops. They are not the tops of the they are chronostratigraphic and biostratigraphic, arranged according to the biostratigraphy. And so the qStrat process actually, I will go forward and then come back to this slide. So the automated sequence stratigraphy is based on the Ainsworth work from Australia. The bunch of work published in AFEG and Journal of Sedimentology, that a lot of manual work was done in order to define how the sequences change from where they are. Either they are prograding or retrograding, or retrogradational and gradation. So by looking at vertically, what you can actually tell if they are retrograding or prograding based on the change in the sequence, the thickness of sand, or what we call it, the thickness ratio. So it is the sand ratio, which is rate of sedimentation, which is sand fraction of rate of accommodation, which is the total thickness. So thickness to sand rate of sedimentation can be defined based on each of the parasequence. So if you're picking the parasequences, then sand to shale ratio is going to, if it is decreasing, it means it is retrograding the system, and if it is increasing, increasing upward, then it is a prograding system. So that is the what we did. Like now we go back to our process. We did a background. So we did two filters, very hard filter, but preserving the like sand and shales, and then a background filter, which is actually just a linear trend. You can use a straight. What he uses is a straight filter, but in order to get all the sand shale combinations in a much smaller details, we need to run a kind of a background filter, and that is again Savastri-Vallai filter. The difference between the two gives us the red lines and the blue lines, which are really crossing, which is saying anything to the left between the two filters, the difference is the sand, and on the right it's shale. And then from each red to red line, we can find the ratio, and that would give us the fifth order sequence stratigraphic surfaces or sequence stratigraphic intervals or parasequences. Now, in this, you can also define your filter size. So you want to be refined within the second wide spec. If you're looking for a really smaller interval every 1,000 years or every 500,000 or 5,000 years, then you can go into the order 6. So this is a loosely used the order name called fifth order, but then we have a process to upgrade those orders, and I'll cover that later. So this is the parasequences and how we can define those parasequences. And now we're doing further advancement into how to get the unconformities, finding upward sequence to be separate from coarsening upward sequences. And so we have further modifications and algorithms keep on going on in order to get all the unconformities and those in place, because this is applicable very good in the shelf environment and the offshore environment. But then as we come to the fluvial part, we would get differences in defining output sequence and how to treat those. So there are all that details going into this. So once we have that first fifth order sequences, then we are seeing that if the ratio or TSF changes like toward more sandy to shaly. So if you get a less sand and more sand, as you got shaly, sandier, then all that total package will become single sequence boundary. So you're taking that into the fourth order as a single sequence boundary, and then finding the total sand shale ratio of that package or the sequence set. So each sequence set then sand shale ratio will give us now the second fourth order. So with the fourth order, then we can further up take the mean and further convert into the larger orders. So what happened by this factor, when we come back, we start seeing that we are pinpointing to the areas where the major sequence boundaries come in, like we can here view. And then at the same time, we put in the Hawk sea level curve and a local sea level curve. In this case, we just put the Miller sea level, but you can build your own sea level curve based on the looking at the geomorphological features and those. So you can build the sea level what it was for certain formations. And of course, literature helps, and qStrat and various other core information comes in to define the next sequence, as well as transgressive regressive cycles can be picked on the log or can be generated automatically from the QSS patterns. So from QSS, you can then these lines, which are defined as the boundaries of the parasequence or so maximum flooding surface and sequence boundaries for third order or fourth order sequences. So usually we use third order for that. So there are a lot of further. There will be a paper published hopefully recently, as well as we're presenting in few other in more detail. So that being said, like we haven't like now the automation process also requires the top picking or testing the top picking, which is what we are developing is the called qStrat correlation top picker. So in this case, we are using a correlation thresholds between log to log. So you go from one log to pick a reference log, as we did in the previous case, and then run it on all the logs. Right now, we're using geological tops to compare with. And what you see is that in our this is the difference between geological top and the although it is a very low correlation threshold, but this is the correlation at the bottom, and then how many meters you are different from the top. So each of the top, these are all the tops being used, but individually, some tops with have a high correlation, they do not have any problem in within 0 to yeah, it's under 1 meter. Most of the histogram comes under thousands of tops picked within zero point 0.1 meter, and that is comes actually equal to human error, like on the geological side when you're picking in any of the software you're picking, but computer will pick according to the hour defined, and it's based on one well. So now we can define more than one well as a reference well, or computer will tell us that if the correlation is low, it can output the correlation map, and that would give us the option to look at that which well should be used as a reference or should be added more than one well as a reference. So it's a really very robust algorithm with a lot of working. If you look at like this is the reference well, so it will output on the reference well. Of course, correlation is 1, except few. But when once you come like a 0.6, 0.8, when you see a 0.8 correlation, the original tops versus the auto-picked tops. So these are on the left are auto-picked tops, while on the right are the original tops. So it for a comparison reason, anything above 0.8 or 0.6, it comes up like with very strong correlation, and but it doesn't at the places it may not pick it. So that is where you come in and refill based on the age and then the original, because of course you will not have these tops to compare with, so you're working with the one or two tops. So that is a huge coming up with these test data set. We are comparing with the original and using different logs as an input, and then comparing. So there's a lot of research we are doing in order to make it improve. It's a combination of the correlation algorithms and neural network based algorithm, and combining with the age assignment, because we're assigning each top as a age. So unconformities come into place, and then unconformities need to be picked when the logs are the tops are truncated, and that is a lot of research happening right now. So looking at the one reference well, you can see these are the in the teapot dome data set. You have a lot of these continues with a very good picks throughout these. I mean, this is just a subset of the 1,000 wells got picked from one log, and we had the correlation like some of the coarsening upward sequences and those various flooding surfaces, we have a correlation up to 99% matching with the whole data set. Although it's one big structure, but the stratigraphic, you can see how computer is easily able to continue those data sets. So it's really very robust auto picking of the tops. And then also from the auto picking output is also testing. Like so your test is that you can have surfaces directly mapped in a 3D. You can view them, or in 2D maps output. While the error maps, you can also generate the error maps and the interval maps. So right now these are the surface maps, but you can also have output the so where it is really going is that if you have auto picking all the way, then you can have maps which you can take the resistivity within those two, like the Cardium top and base, uh, like and output the resistivity in a wider area throughout maybe whole Alberta. So so it would take any attribute, can be porosities and those. So you can actually treat these as 3D, because there are so many well penetrations, especially in Western Canada, or many of the old fields. So we will target like this is the old fields which have probably leftover pay, like how to get that out through this process. And so just, and also in the cross section, then you can start either auto interpret using the QSS, or manually interpret, and then you can actually take the flooding surface and then say, okay, this flooding surface is equal to this. So you can actually either interpret with manually, or have the tops move and have the age. Again, age is tied to the tops, and it's adjusted according to the unconformities and those things. So that going to there, like you can have a larger cross sections, and then so basically starting from the log data all the way to cross sections and maps and individual well log uh, display, well log interpretation of the qStrat. That is our workflow which we develop internally to help our clients with giving us the set of log data and header, and of course many other, like the information which we are going to use then would be the perforation and those, and production information to help where to steer with, where the bypass and new pays are. So but it makes the workflow of geological interpretation much easier. And that's where also we bring in here, the next step would be to where our development is going, taking the faults and then creating the relative geological time, because you already have absolute geological time from the wells, or at least the assignment to the best of your knowledge. And then we are going to take the relative geological time, that is another sequence stratigraphic interpretation of the seismic, and then merge them together into a making it absolute geological time, so that the interpretation can be corrected based on the logs and the velocity models and all those things, as I said in the whole workflow before. So I'm just concluding, and the work ahead. I've left blank because there are a lot of lot of things to do, work ahead. But the manual sequence stratigraphic workflow is very time consuming, and that's why people do not use it most often and call it a research project and leave it for the for the research, which makes it very problematic, because anyway the geologists in a exploration team have to do the make the decisions, and he need that sequence data. So geologists are usually scrambling through the data and not have a cohesive workflow to like cohesive tools to be able to manage. So that's where the future is going to, like big data, and you don't have time to look at every curve and look at these. So deviation curves, log data, and all associated files, and these should be organized. We could not just depend on some of the providers to clean up for us, because every exploration company does have to go through and clean up their database. So very help in the database management, as well as the log data, what we have, what we don't have, what we need to shoot. Sometimes people are just shooting new data because they don't know that the existing, where it exists. Like we bring in from DLIS files and LAS files. So DLIS input output as well as LAS. Many times people don't look at DLIS files, although many of the data is not converted to LAS, because all the wellhead information, log information, which petrophysicists need, is hidden in the DLIS file. And now then you manually trying to put in your petrophysics tool, which is prone to errors, as well as somebody else put in the header, which is prone to error. So our log data management allows it to put it more together. So anything which is have a doubt or uncertainty in the log data, or can be thrown out or sent back to the geologist to look at. So every stage, this whole process can be run without looking at anything, but at every stage we can look at the results and then rerun the process, either 1 or 6 stages or whole of the workflow. And they all are allowed for 1 well, for 500 wells, or 1,000 wells, or 5 wells. So it's a fully flexible, and we test on 5 different data sets with various number of logs. Uh, so so it is a few clicks to go through the process, and then actually you can go through automatic process to the last, and then come back to rerun, because in the process you will find the errors in the cross sections and those, and then come back and run in the log QC. Look at, so at log QC can be run at every stage. So there is a whole tools. So it is done by the geologist, supervised completely very closely by the geologist. And that's what our team is. So whole developers and geologists sitting together, geologists, geophysicists sitting together to have, we've dealt with these problems for last 20, 25 years, each of us. So that's where we are trying to solve our, just help us do better, better work. So that is, thanks for zooming in, and we'll try to put the recording on the YouTube channel as well. Any questions, you're welcome to ask. You can go back or close. Mhm. Okay. Yeah. Everyone is muted, but I can unmute everyone. Nah.